Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, optimistically, I assume the room is now half full. I'm really pleased to introduce Luc Blaser, who completed his PhD at ETH in Zurich fairly recently, and I had the pleasure to read his thesis and thought I had to invite him over for a talk. As you can see, he's going to talk about a component language for structured concurrent programming, and I don't know how honest he'll be about his own achievement. So one thing that I found very impressive is that he built the entire stack. He designed the language, he implemented the language, he built the runtime, designed the runtime, built a significant application in that language on top of that runtime, and then dared to performance benchmark it against, if you like, commercially available solutions. I don't want to sort of take too much of your thunder away, but that in combination left me quite impressed. So it's my great pleasure to introduce Luc today, and I hand off to you.
Many thanks for the kind introduction. So good afternoon. As already mentioned, it will be about a new programming language and its implementation. It's actually a component-oriented language for the target or the aim of structured concurrent programming. So the motivation behind this work is actually, as far as I believe, the current state of the art with its major manifestation of the object-oriented paradigm that has, however, in my opinion, three, let's say, major problems. First of all, the references are, for me, a rather unstructured concept that reminds me on let's say, the go-to statements. It's something that allows you to arbitrarily interlink object instances without having a clearly specified resulting or a clear specification of the resulting shape of the object or the object network that you gain at runtime in your program. And the result is that if you want to model hierarchies or something like hierarchical encapsulation, an object that is to be composed of other object instances, of a structure of other object instances, you can model that, of course, but it's not guaranteed by the system. It's not guaranteed by the language. So you can accidentally construct a link or introduce a link that somehow falsifies your intended hierarchy. And this is naturally, the consequence is that the runtime structure of an object-oriented program, as it is perceived by the runtime system, is always a flat graph, a flat object graph, because every object instance could be potentially linked to another object instance, as long as the types match, of course. And therefore, for the runtime system, it has to go to start or to be built with this principle that you have a flat structure. And if you want to model hierarchies, then this is just the thought of the program, and it's not something that is ensured or guided by the language and the runtime system. The second concept is the concept of inheritance that is quite frequently used. If you observe it, it's a combination of two purposes. The first purpose is the purpose of type polymorphism, that we want to use this concept to somehow have an object instance and use it by multiple static types, somehow to use a type that is only like a subset of the functionality of the eventual object. And the second purpose is the purpose of implementation reuse, that you use inheritance to somehow reuse existing functionality implemented in these superclasses, in the base classes. And these are two purposes that often just fit together, but sometimes they also do not fit together. If you have like a square and a rectangle as a class, modeled as a class, then you may model it as the square. In the mathematical way, you would say the square is a special case of a rectangle and nothing else, and you will model the square as a subclass of the rectangle from the perspective of the type polymorphism. But from the other way around, you could also say that the square is something, just a part of the implementation of the rectangle, and this would then be the false way to use the inheritance, just to to make use of the implementation reuse. And the implementation in existing language also shows a little bit these limited possibilities, that it's either only offered as a single inheritance construct, that you then, if you have multiple equivalent facets of an object, then you have to decide which one of them is like the major or the most relevant one to be modeled as the base class, and which should be modeled by another concept, interfaces, for example. Or you have a multi-inheritance support that has then its well-known problems, like these naming conflicts. Diamond problems are just some examples of that. And the third issue is actually an issue that is becoming increasingly important in future. I think that is the rather poor support of concurrency, because concurrency is something that has been nowadays, whereas in Simula, the original object-oriented language has been offered as a primary language concept, a primary concept of the paradigm. It nowadays has become that the objects are mere passive object, and upon them you use the threading mechanism, a special, a second-class concurrency mechanism that then operates on these purely passive objects. And the problem here is, of course, that these threads, because of the method calls, these threads can operate on, let's say, on arbitrary passive object instances, without that it's clearly specified in your program or in the language what is the set of potentially accessed objects of a thread. And therefore, the result is that threads may accidentally collide, that they have uncontrolled overlapping, what is often called race conditions, but also because due to the flat object graph, and also because of this second-class setup of this threading mechanism, it's also the deadlocks and starvation problems are inherently promoted, because the structure of the potential overlapping and ways as thread may operate through object via method calls is not clearly specified. And also methods are something that are a little bit unnatural in a programming model where you have objects that have an interaction mechanism, because the methods are always blocking, and sometimes it's not understandable why, because it's like if you send somebody a message and then you have to wait at the post box until the message has been received on the other side. It's somehow unnecessarily like excluding concurrency in a primary programming concept. It's just the procedural notion that has been institutionalized in the currently most prevalent object-oriented languages, so to say. And so the approach has been to create a new programming, or a programming model that is from scratch newly designed and just offers like making a tabula rasa and using and thinking about concepts that would maybe better suit for these problems, or to address these problems. And the language is only based on a general object notion, which is called here a component concept. And the primary kind of or the primary characterization of a component is that it is a general and abstraction unit at runtime, which encapsulates both state and behavior. State is something that can be modeled, for example, with variables, and behavior is what are the interactions between the components. And the kind of the principle of these components is that strict encapsulation is at the heart of this language, that all dependencies which a component has have to be openly specified and only via interface. This is actually what can be considered as the traditional or the consolidation of a component concept. And in this language, components can therefore offer and require interfaces. The offered interfaces are kind of the functionalities being represented outside of or kind of a facet that is perceivable outside a component. It's a functionality that is offered by the component, and the component may also has to also specify its required interface. That are interfaces which are offered by other components, and the component may requires or has need of it in order to operate correctly or have sufficient kind of primaries support to operate. And analogously to the class instance concept, components can be specified by a template, which then allows us to create an arbitrary number of instances by it. And here this template, for example, illustrates this a car that's maybe perceived by two external interfaces, the vehicle interface for driving and luggage space. Maybe it has also some space in it that can help us to stow some article items in the car. And the required interfaces are interfaces that the car may require in order to perform its usual functionality. And the component instances need to be statically declared in this language. It can be very simple, like car1 and car2 being two instances of this template car, previously shown. And but however, often this kind of static fixing of the component template is not very reasonable. It is often useful to not fix it and rather postulate it in a polymorphic way by only denoting or by only stating the interfaces which are somehow to be offered or may be required by a component. For example, here we have a vehicle component that can be any component, a component of any template, as long as the template has to offer a certain set of interfaces. So the component may offer more than this vehicle and luggage space interface would be still feasible within this declaration, but not less. And on the other side, the component, this is actually the dual part, the component should not require more than this required interface, because then it would have some kind of hidden dependencies to its environment. So if the component if it would be a car without a radio system or a navigation system based on radio, then the component would also be feasible if it would only be a radio. If it would only require the road interface. And in this language, instead of only having a concept of arrays, the language offers a generic collection of components. Here we have a collection of cars, of instances of the car template that are to be identified by an index that is here a pair of the state name and the plate number, for example. And this then allows us within this collection to allocate or to use a dynamic set of components. The components have three relations which govern the structure. First of all, hierarchical composition. A component is able to very simply consist of other components, consist of a dynamic or static set of subcomponents, which are to be fully encapsulated and only controlled by the surrounding component instance. And using this mechanism of required and offered interface, it's possible to connect the interfaces of the same name, such that we can create a network of component instances that are, however, to be encapsulated or can be encapsulated again in a super component. Sorry. And the third mechanism is that these components have their own kind of implementation and only interact by way of a decoupled mechanism, of disentangled mechanism of sending and receiving messages, a message communication mechanism. And therefore, it is inherent that the components somehow run independently, because they just are not blocked while sending, or not necessarily blocked while sending or while interacting. And therefore, there is an inherent mechanism of concurrency, because it is not prescribed that components have to perform any kind of method calls, for example. Just to outline how a component may be implemented, here it's again the car component, which has a set of variables and a kind of an internal behavior, internal setup sequence. Well, the behavior here determines the setup sequence of the component. And the variables in this language are something like containers for variables, or separate containers for variables. Here we have the variable engine that is able to store one component of the template big N or capital engine, and here we have a collection of wheels, which may here be a static number. And then the setup script, for example, can also then allow to create, for example, component instances and connect their interface. Here, for example, we have the engine component that has a required interface gears, and this interface is then, by this statement, connected to the offered interface gears of the gearbox, for example. And the same is applies for example, the wheels that are just in this kind of illustrative example, for example, connected to the gearbox. And in this language, it would be also possible to connect, let's say, outer interfaces, that the super component connects the outer interfaces to the inner interfaces, and also required interface may be kind of forwarded outside. Yeah, please?
So are these connections only made at the time when you instantiate this template, or can they change?
They can also change. That's what actually the next slide, or the next slide should show up. So here it is, by this way of example, it's just something that can be perceived as static. So a static setup of a car component. But the kind of the transition to a dynamic scenario is just right in the same way. For example, here we have a traffic simulation that creates, for example, a dynamic number of cars. So a number that is, for example, determined by an external XML file, for example, or something that may be underlie a random number, or whatever, the space of locations within this simulation setup. And it's actually the same way. It does not matter whether it is a kind of has more dynamic characteristics or static. Here we create the road, a news center instance, and then repetitively, for example, just here we create cars until it's decided that there are enough cars. Yes, please.
Can you say more about the new operator you have there in terms of if a component is identified only by the interfaces that it requires and supplies, how do you specify what is required in order to create a new instance?
Of course. Yeah, here, for example, here it's the very simple, as you all have already seen. It's the very simple instantiation operator that just creates a new instance of this template type within these variables. But however, if I allow to scroll back a little bit, if we have something like this polymorphic declaration, then with the new statement, as second parameter, we specify the specific template of which the component should be created. So this would mean here, if we just specify road is something that offers the road or the road network is something that offers the road interface, and we have here like an any construct, then we say new road network as second parameter. Yes?
When you create this new road, is it producing messages before these other things are connected in?
No. That's what I should come later, but I can already just briefly mention it. The components are only able to interact by message communications whenever their interface is connected. As long as the interface is not connected, the messages are just blocked with regard to this interface. So if the car, for example, it's a little bit unnatural, sends some messages to the road, and the road is not yet connected during the setup or during the previous setup, then just the messages are queued until or the messages up to a certain level of the buffer are queued, because it's kind of transparent whether the message sending is non-blocking or blocking, because it just shouldn't matter for the time perceiving of a single component. Yes?
So could you reconnect the car to a different road?
Yes, this is also possible. It's possible in this language also to disconnect, but then I will come later to that. The components will exchange messages according to a protocol, and then the protocol has to be completed for allowing like a shift to another connector. So a little bit here, it's this way of interface connection looks similar to references, but it has some subtle differences. That is that the interface connections are always connections to be set by the surrounding component. So that there's a hierarchical control upon creating the interface connections, whereas for references it is just something like a value in an object-oriented language that can be copied around and therefore allows to somehow create arbitrary structures, and therefore, because there's no limitation or no kind of guarantee for an intended hierarchy, then the system has this flat object graph in the end. And these interface connections are dual connectors between incoming and outgoing connection points, such in contrast to the references, which are something like an asymmetric link that directly leads to an object, without that the object is maybe kind of willing to accept such a reference. And this at the end then leads to a runtime structure that, as I would say, is more general than just a flat object graph. That is namely a hierarchy of component networks. So every component is able to again contain a network of arbitrary shape of subcomponents in this language, and therefore we have a hierarchy in this programming model. And this then also allows us to do a little bit rethink the existence of an object or a component. Whereas in object orientation, it's just say that with garbage collected systems, the object, we have control for creation, but not for deletion. And the existence just lies in this postulation that whenever it's not reachable anymore from a chain of strong pointers from a root, then it's not identifiable anymore in the system and therefore can be removed. But this is not the perfect mechanism of collecting object, because an object may be kept referenced by accidentally kept reachable and nevertheless would be never used again. And here in this language we have something like hierarchical lifetimes. So if we delete a component, it's obvious that the subcomponents are no longer be directly accessible from outside, and therefore we can immediately delete the subcomponents as well. So we regain possibility of exploiting the hierarchy for also the deallocation mechanism. And here it's also possible to explicitly delete the component, that we say, oh, this is an old car, we delete this component, and then the interfaces are disconnected because of this dual mechanism, and then the component will be removed with its subcomponents. And therefore in this language we have something like a memory management mechanism without needing a garbage collector. And we do not have any low-level dangling pointers, pointers which immediately lead to memory that is no longer allocated. We can have something like a component that has a disconnected interface, but this is safely managed in the language and the messages will be blocked, but it's not something like just mere addresses leading to a non-allocated space. And the mechanism of concurrency or interaction is that, as already mentioned, the components have their own lifetime scenario, and therefore this lifetime scenario and will interact by message communication, and therefore the components can be concurrently executed. So it remains on the decision of the runtime system which degree of concurrency can be or should be exploited. And therefore, from the perspective of the programming language, every component has its internal logic that runs concurrently and only interacts by exchanging messages. And here, for example, if we consider this example, then the component which offers the interface can be considered with regard to this interface as a server of this interface, because it offers it, of this communication. And the cars are something like clients because they require this interface. And in this language also it is an inbuilt mechanism of using separate communication channels, so to say, with every client individually. And this is, I will illustrate that later, as already mentioned, this with the stateful communication, but the components cannot arbitrarily send messages and receive messages as they like, but they have to fulfill a kind of a formal protocol, a communication protocol that is to be specified within the interface. And this protocol is using a notation that is also known or is similar to it, or is actually EBNF, that's an extended Becker-Snauer formalism that is, in my opinion, specifying in a very compact and still readable form this protocol. Here, for example, we have a message request news that is an incoming message from the perspective of the server component. So the car component has to somehow deliver via the radio interface notification that it is interested in receiving some kind of, for example, traffic information. And then, denoted by these square brackets, this denotes a repetition of 0 or arbitrary many times, that this sub-expression of EBNF will be executed or will be needed to be executed in this. Yes?
Sending a message can a process have side effects? Any other side effects, are they possible?
Sending a message?
Sending a message. Are there any other side effects that are possible in the system?
Except that it can be received or should be received on the other side, not. from the perspective of the single sender component. So then this under like this sub. So in this example, then the traffic center component will respond with a few messages that are either a jammed, that it denotes that there is a jammed road link, a newly jammed road link, or a previously congested road that it has been that has cleared in meantime. And this continues as long as the server component does not send this end of news message. And then this communication is, or this protocol, or this interaction, stateful interaction, is terminated. Just to sketch the implementation of such a protocol, we have the client just performing maybe within its internal lifetimes, internal implementation, performing this send and receive statement using the CSB-like notation. Here we have a receive statement and a syntactical expression that is just a receive test. So it's a little bit written in the same way, but here it's really a syntactical statement. In this language really distinguish between statement and expression. Here this is if something is just an expression, and this is a statement that can't be mixed up unlike C language, for example. And here we just test, is there the next arriving message of the type jam? If yes, then we accept or receive this message within this implementation. And the traffic center component is the component which offers the interface, and therefore the server, and in this example, should be able to maintain a stateful communication with any client separately. And therefore, we have here such an implementation block that implements the offered interface, and for every client, a separate instance of this implementation block is incarnated and then runs as a syntactical, let's say, a service process within the traffic center component, for just performing the server-side communication with the individual client. And as we already see, between components, there's no kind of synchronous synchronous execution transfer. So the processes just run within a single component. But however, in case of such a server component, we have multiple such internal process, because we have multiple client services. And therefore, because the communication protocol is inherently kind of synchronized, because the send and receive is a disentangled interaction, we only have to concentrate in this language on explicit synchronization within a component. So in this language, we have the possibility of using like usual monitor synchronization within a component, and we can state explicit and shared exclusion directives, and also use something like a wait statement that waits on the fulfillment of a Boolean condition. And therefore, it's very simple for the compiler to only perform an intra-component analysis to determine whether, let's say, the accesses on shared component variables, for example, are sufficiently protected by exclusive or shared locks, such that this very low-level race conditions are excluded in this language. Just to summarize a few maybe extra features of the language already mentioned, this encapsulation, where it's also allowed that the surrounding component can forward incoming exterior interfaces to inner components, directly link them. And it's also possible that the component can require more than one interface of the same name. So if there is a kind of a hotel, then we may have multiple phone lines, for example. This is also possible. And within the messages are able to have parameters that may be simple data values, but can be also components, so that we are able to somehow detach a component, like disconnect its interfaces if they are connected, and then ship, so to say, a component within a message as a parameter to another component. And this, yes?
When you receive this component, it automatically starts running, because they all have their own threads, right? Or
yeah.
thread of control.
It actually will start running when it's created. So you have to already have it pre-allocated, but if its interfaces are not connected, then you won't perceive it outside the component. And therefore you can somehow ship a running component, let's say a running engine, for example. But the engine won't have any side effect if its interfaces are not connected. So if you create an engine and there's some internal logic, let's say a setup script that has no external effect, then this can happen. But as soon as the engine wants to somehow connect with the gearbox or to perform force on the gearbox, then this won't have any effect until it is, for example, received at the car, in the car and connected with its surrounding, and then can perform, for example, force.
Isn't it possible that you get race conditions due to a component whose thread is running and is producing events, but then you're also connecting to its interface? And now it would matter whether you connected to the interface before it produced an event.
No, this is actually handy, but this is an important question when you create the runtime system for it. Then you have to address such subtle synchronizations due to the mapping to a simple machine. But from the perspective of the programming language, the messages are just in this buffer blocked until it is connected. But when connecting, the runtime system takes care of this fine granular synchronization, that the messages are then, as soon as it is connected, properly forwarded, and nothing is lost or nothing getting stuck.
So if you connect only one outgoing interface and another one is still disconnected, can you start seeing messages on the first one that you did connect?
So if you have a pair of partially connected, yeah, this would be possible. Yeah.
So then doesn't it matter, I mean, independent of the runtime,
which order?
Yeah, which order? It seems
no,
like
it's actually a component should not perform something like multiple ways of, if you have multiple sending, you can perform multiple sending in kind of a sequential order, but not in this multiple parallel order. So otherwise it would matter if you have like a component able to send in one time a message over channel A and then in parallel a message over B, and then only one would be received. But if the component is just executing like a sequential protocol of the main process, of the main transmissions, and then it's natural if there's only one interface connect, then this can go on, but then with regard to the second interface, the connection won't continue. Mm-hmm.
So looking at sequential reuse, let's as an example, if you're implementing motor, do you have programmatic knowledge that wheel is connected or propeller connected, and base your logic off of that?
And also to see whether we are connected, yeah. I don't know. Also, I have not offered this in the language because I thought it should remain transparent, this environment. But I'm not sure whether this could be. Because if you have, as soon as you have something like, can I send, this way of expression, then you come into these problems that you don't know on which interface should I send, and so here it's really, the assumption is that the component is fully connected in order to operate. But it's a good question. There is, with regard to such multiple interface, there is this mechanism that we know.
Situation where you might implement motor that actually has a dying philosopher problem, where the knife and fork being your wheel and propeller.
Yeah, I did not say that it is solving any concurrency problem. Deadlocks can still be designed with that. You create a cycle and then construct a protocol where you run into such cyclic decision problems and then can't continue any longer. And then also, as already mentioned, with the interface polymorphism, we have something like multi-inheritance in a lightweight form, that we can only use it for polymorphism and do not have to only use one of those amphibian mobile that has a road vehicle and water vehicle interface, and both are equivalent. You can't say the one is more important than the other, then you can just simply model that like that, this like that. And the polymorphism, like this first purpose of polymorphism, is clearly separate as a concept from the mechanism of reuse that is here in this language. I've intended that this should be enabled by reusing components and connecting it to their environment. And the language also, for kind of interoperability purposes, there's this clear separation between interfaces and implementation that is at the principle of the language, and therefore it would be conceptually also possible to implement terminal components, so to say components that are not again containing subcomponents to be implemented in any other language. This is a trick for building this bridge with other systems, with other languages. And it's also used with regard to the implementation, that the kernel is implemented as such a component, and this is implemented in a more low-level language that maps better to the underlying machine. And so we are directly here with the runtime system. So the language is implemented. It's not only like a thought or a thinking activity. It's also implemented with a small kernel. Operating system is exaggerated. It's something like a small kernel that is directly executing on the bare machine without underlying operating system except the load. And it's designed, of course, to efficiently execute this language, which has some substantial differences with regard to the resource requirements to classical language, because every component needs to be or should be in the programming model be concurrently executed. You have a completely different requirement for your system, whereas classical systems are somehow optimized for efficient sequential or procedural execution. This system should be able to execute a large number of processes, a large number of these internal or parallel components, and therefore the system offers a concept of lightweight process that has dynamic microstack. I will go to detail in the next slide. And also the context switches between these processes have to be particularly optimized. And I just mentioned this here. The system also has inbuilt synchronization mechanisms, like this communication protocol is dynamically checked and implemented by such a buffer that is behind the scenes, and also monitor synchronization is already inbuilt in the system. And memory management, as I have already mentioned, this with the hierarchical memory management can be simplified. Also, here it's no virtual memory needed, memory management needed, because all these components can run in the same address space, and therefore the system does not have any virtual memory management. We'll see later that also the virtual memory management will not help for the implementation, for example, of the stack management of processes. Just to very briefly say these processes, so every process, like every thread, it can be compared to a thread in the usual terminology in operating system. Every thread has its execution context that is stored in a stack, and in this system, these processes are able to have an arbitrarily small stack. The stack can be, the size can be even smaller than page granularity, so it can be only like a few hundred bytes or a few bytes, and this is able. And therefore, it's no longer based on this virtual memory mechanism, because we have to get smaller than that. And the stack is also, with regard to extensions, at runtime, it's no longer represented as a contiguous pre-allocated virtual memory space that is then just ad hoc, the real pages or the real frames being allocated. But here it's implemented as a stack that can grow at runtime or shrink again by representing it as a linked list of blocks. So it's the separation between stack space and heap space is also no longer. So it's not in the system anymore. Here the stack is something that is allocated on the heap. And for the components, as we have already seen, there are no method calls, but communication interaction. Therefore, there is not an arbitrary deep, as long as there are no procedures used within a component, there's no procedure call, and therefore it's very simple for the compiler to pre-compute the actual size or the actual context, the execution context a component needs to execute its internal process, and therefore the stack size can be better pre-computed and therefore pre-allocated, such that there are usually no runtime extensions or reductions of the stack needed. Yes?
What's the minimum size, the minimum amount of space you need to allocate a component?
The minimum? Yeah, this could be for example, I think 8 bytes are sufficient because you need a pointer to the component. The process needs a pointer to the component, and maybe 4 bytes, I don't know. But it depends on how many variables and how many space you need to execute its internal logic. If you have something like complex logic and need to have temporary evaluation of expressions and so, then you need more. And we'll come also later to this. Also for context switches, we need some space, of course. So this is more technical, but very briefly, this is implemented here. If a component would have internal procedure calls that wouldn't be visible outside, then this is here done in this system by that the compiler inserts for procedure calls and procedure returns extra code that then performs the allocation of extra blocks and then shifts the stack pointer to it and then passes the parameters and so on. And an often scenario is that a component can be interrupted or can be at any time there can occur an interrupt, and the interrupt of course needs some space, and it's not reasonable to pre-allocate this space on the component stack. But for these interrupts and also for frequent system calls, they are executed on a processor stack, on a system stack. So every processor in this system, and the system should have a static number of processors, has a pre-allocated system stack of sufficient size that is just there to execute this internal procedural calls. And they have to fulfill this principle of run to completion. So they have to be fully executed until the execution the corresponding processor can continue its execution with the ordinary processes. And the context switch is also very simple in this system. They are behind the scenes, the synchronous context switches. These are those which are, for example, happen when a component waits for a condition or a message or a receiving message, for example. Then this can be implemented by an ordinary procedure call, the system call behind the procedural system call. And the programming language is designed to be memory safe, and therefore in this system there is no strict principle of separating the kernel and the user space is not enforced here, because it's really assumed that the programming language should not somehow override the system memory, and therefore it can be this shift to the kernel mode to switch the kernel level threading, so to say, is not here. Implement or not needed here, and therefore such a synchronous shift can be such a synchronous context switch can be very efficiently executed. Here's just illustrative how simple this can be by exploiting somehow the procedure prologue and epilogue just for performing the backup of the corresponding synchronous state. So I can say a little bit more about that. So the procedure prologue will usually store all let's say variables that are still in temporary use on the stack, and then we'll also store the instruction pointer, the old frame pointer, and by just shifting the frame pointer we shift to another stack, and this stack is in the same format. It's also backupped in the same format, and then by the procedure epilogue this state can be restored, but on a different stack, and then this can continue again. This is not my invention. This is just to show how simple this can be, for example, implemented. And the preemption is a little bit more, let's say, advanced or experimental. This is the asynchronous context switch that is in this system no longer only performed by the hardware, by the timer interrupt, but somehow supported by the software. And the goal is that a process does not need overly space for storing all registers on an asynchronous switch, because just this extra backup space will be already a substantial amount per process to store all registers for an MMX and SSE2 these registers are often not in use at the point of an interruption, and therefore it's not very reasonable in this system of very micro stacks to perform a full backup on every preemption. And here it's done with some preemption check. It's still called preemption, but with some checks that are inserted in the code such that these checks are executed in guaranteed small time steps. And therefore, it's obvious that for every loop, we need such a preemption check. And for every kind of procedural invocation, as we can have recursive invocations, for example, we need such a check. And also for sequences exceeding a certain maximum time, a maximum verse time, we need such checks. And these checks are just there to, in sufficiently small steps, check whether a certain time slice of the process has expired, and if so, these checks immediately perform this kind of synchronized preemption. And the purpose is already, as mentioned, to only store what is necessary, because the compiler, and this happens only behind the scenes, so the programmer does not see anything of this. This is just something that is compiled by the compiler into the machine code, and is transparent to the programmer, and the compiler then knows which registers are in use, and by just putting these checks at reasonable places, maybe mostly between statements, it is actually nothing to be, or nearly nothing to be saved. And therefore, and this is what my original intention is, to not have any separate pre-allocated backup space, just to have a full backup set for a register. And the checks are very simple, as the processor pipeline is mostly underused if memory access are performed, such that with regard to my example, which I used and to which I will come later, it's really a very nearly not remarkable runtime overhead just to perform these checks. Just here, this is a kind of a benchmark that is not so, relevant, because it's just a benchmark with toy examples that are just showing a little bit, giving a flavor of the system that is optimized with regard to concurrency, but not, let's say, to sequential programming. And therefore, the focus is here also on processes and concurrency. This, as already mentioned, the system is able to execute a very high number of processes. Here it's a very simple, an example of houses that consume and produce or need resources, a small toy simulation. And it's here observable that the system, that the amount of processes that are supported by the system depends naturally on the real memory space that it's offered, because this determines how many stacks and processes can be allocated. But it's also that it depends on the complexity of the components. If the components require more space, then certainly the number will decrease. And ordinary systems have, of course, this problem that the stacks have this conservatively pre-allocated virtual space, and will run out of virtual memory space. This is a little bit let's say, interesting to see that not the real memory space is becoming scarce, but the virtual memory space, so to say. Because then the address space, just to perform this contiguous growing of the stack, will then be the limiting number. And it's also in the existing system, it's difficult to say, will a thread need 100 kilobyte or 30 kilobytes? It's always either too small or too big. So it's either running out of the stack or being a waste of virtual memory. Yes?
Are your comparisons against 32-bit operating systems or 64-bit operating systems?
This is just 32, unfortunately. Yeah, because 64, this is true, then this virtual memory space will not be of any matter anymore, because then we have so much more space. Yeah, this is true. But still there's this need of also having not only the virtual space for performing the stack overflow check or allocate, but also the real memory is a problem, because then we need, for example, 4 kilobyte real memory per stack, because we have to allocate in page granularity. And this is also would already be a problem that would spoil this goal here. And also, and this is also a little bit subjective, so to say, this is naturally like concurrent programs that are really relying on frequent interactions are substantially more efficient here, because this it's just these context switches which are particularly optimized here. If we have something like a Mandelbrot problem, then this is not so fast because the sequential execution is not so optimized. The compiler is a rather simple one-man compiler, and it's here really concentrated on fine granular, frequently interacting concurrency. And you will see just now why this is necessary. Here, the goal was this language has been intentionally designed for this kind of rather abstract goals of improving this or giving a different view at the object-oriented programming model. But it's also kind of validated by a practical, substantially practical example, that is a traffic simulation. And the idea was, because object orientation was invented for simulation, so it's somehow obvious to also use simulation as a kind of a test case. It's a good test case to evaluate kind of a new object-oriented language. And here by the TU Berlin, they have such a department, or such a research institute that which performs simulations. They have, or actually I have supported them in building a new traffic simulation that has somehow two goals. So the goals of this project were two, namely to somehow evaluate what is the benefit of modeling with regard to the simulation. That was the primary goal. And the second goal is the more simple or the more technical goal. Is there a possibility of having a faster simulation due to this maybe new modeling, and maybe also in comparison to this thread-based systems that are somehow by advance not designed for this purpose. And this language obviously somehow supports this more initial thinking of simula, of really modeling components or objects also as active instances. Whereas in classical traffic simulation, as they did that, the cars were modeled as passive objects that were somehow moved by a central scheduler, self-programmed scheduler that from time steps then moves the car, for example, across junctions and so on. This is this discrete event simulation by a single self-programmed scheduler that performs these movements. Here the cars are somehow modeled with a self-closed internal behavior. So the cars are somehow performing their own movements and their own weightings on traffic jams, and performing also their individual planning here. So this is things that can be modeled before, but they are somehow improved by the programming model, because this is the principle of this model, that components can have an activity. And the benefits were here that these cars were simpler implement, because this explicit shadowless we can get rid of that. Also, this waiting queues that are often needed. So waiting that the scheduler has to park the car, the passive cars, into a waiting queue to take it out again, can then be somehow, is in this new simulation done behind the scenes in the runtime system, which has then the scheduling of the concurrent threads. And this is naturally, this is in this system more optimized than just using the self-modeled data structures. And the virtual time, there's also this car do not run just by randomly by the speed of the program, but by the computer or the scheduler, system scheduler, but run by a kind of a virtual time axis. So in the language is also something like that cars can wait for a certain virtual time, just that the speed of the concurrency complies with the real observed speed in our natural world, because it's not the speed of the system scheduler that determines the quality of the simulation. And therefore here the simulation is certainly faster than the thread-based, just the same like the analogous implementation by using, instead of active component cars, using a car with a thread. This is of course something that is somehow abusing the thread notion, but also with regard to the sequential, this was by TU Berlin, the sequential C++ implementation, because this has a completely different simulation model. The classical model is something with an explicit scheduler moving over the time axis and moving the cars, because a discrete event simulation is a kind of a discrete event simulation which does not perform bigger time steps, because this would be too expensive to always calculate the minimum time steps. And the simulation is performed with a resolution of 1 second. So really big simulations are here performed. This is a simulation of the Zurich traffic with data used from the government. And then the simulation is also faster than the classical model. But this is just kind of using a different algorithm, so to say, for performing the simulation. Just to briefly conclude before I will show, yes?
Will you be able to infer anything about the scalability given the orders of magnitude difference in the two rows for your system versus the C++?
Here. Here, this here. Now this is here because the system runs over this time axis, and here it runs just over the necessary effects. It's not so meaningful. Here it's just comparing to what they had before, and this is optimized to very large simulation, not to very small simulation. And here it's just kind of a comparison with two different system worlds. And so it's very difficult to say. It's just showing the...
But if you multiply 0.04 by 260, you get a number of about 10.
Here.
So this...
Here. No, here.
Where you have 76.
Yes.
So there's some kind of a nonlinear thing happening in the simulation.
Yeah, that's true. That is because the complexity of interactions between the cars are not linearly growing, because this car, they get into jam. If you have just 1,000 cars, then this just runs through. And if you have 260,000 cars just driving via the central point in Zurich, then you have a problem. Then this can go on and go on and go on. Yes?
So if you compare like with sequential C++, the increase is very small.
Yeah, this is true because this simulation is implemented this way that this goes over the time axis. And if the simulation is kind of or if there are only few cars, then this just runs kind of in idle, so to say. But there's also for bigger simulations, then we also, I did not find any kind of, because you could think here that this is growing in a different, like in a less tremendous scale up, but this is also a problem, because if we have more than these cars, then this simulation is so over jammed or over congested that there's no car would arrive in the end at the final destination. So it's really here, it's something like the maximum exploitation or the maximum capacity of this Zurich network. But it's difficult to say. If you do something like a practical or kind of practical measurements, then it's difficult to compare them, because then you have just the goal of the practical result. If I am permitted, I will just briefly mention some conclusions. So this language has been designed for some conceptual advantages for hierarchically controlled structures. So this is with regard to the runtime structures that have some kind of guaranteed hierarchy inbuilt. And also the concurrency is kind of a primary language concept that, in my opinion, is more structured, because it's somehow contained within a component and no longer being spread out among different components. And the technical advantage here that is the system which is particularly optimized, this bare simple system optimized with regard to scalability and of parallel process, and also the performance for frequently interacting concurrent processes is particularly optimized. And due to the programming model, no garbage collector is here needed. This was also something to see whether there is a different way of having a different memory management that is not less, I would say, less lucid than having a garbage collector. And the practical applicability was the goal of this case study with Theo Berlin that shows that it's somehow a new language, is, as Wicht sometimes said, it's like not only learning a new vocabulary, but also a new world of thought. And it's somehow the language influences your way of modeling something or solving a problem. And this is then different than just using a passive model and then scheduling the cars by, let's say, a central authority that has, like puppets, moves all cars around. And there are also like these smaller examples which show with regard to the concurrency speed up. And at the end, I thought I will shortly demonstrate the system. So the system is a kernel, and it's not so pompous that there is some graphical output, but not tremendous. It's really kept to a minimum. And for this purpose, I will have to restart the system. And I will do a cold restart because this goes faster. And first I will not start into my runtime system, but in the Oberon system, because mine is really only the runtime system and not the development system. So this is also here a little bit how do you say, just because there's no editor in my system. This is ordinary Oberon system. This is something that has been developed at ETH by Wicht and Gugnecht. And here I've just kind of my program text. So yeah, for example, I can show here a simulation that is actually a producer-consumer. Sorry, I will concentrate on my screen because it's somehow unnatural to. Just to show a few more examples written in this component language, we here have something like a producer-consumer example that is a simulation containing other templates. It's also a nesting of the static templates that is not the hierarchical structure at runtime. And here we have a producer that somehow is sending just a certain number of messages. The consumer, this is a very stupid example actually. This computes, this just receives this, the other component receives these messages. There are the interfaces saying that the one side is just sending and the other interface just for the purpose of receiving messages. And there's a bounded buffer implemented with monitor synchronization where we have some like an exclusive monitor lock. We're waiting that a certain capacity is there. This is kind of a self-created restriction. And here we have the data output that just waits whether there is something to deliver and it's not finished. And then we do, let's say, the hierarchical setup that we build a buffer, consumer, produce, and connect the interface. And then we get something like that. That's the very simple example. And then we have also something like a sieve of Eratosthenes. It's maybe a little bit too much to go through. There we have a number generator that offers a number stream. We have a sieve that offers a number stream and requires one, and so on. And then we build this pipeline of that's actually like a design pattern. The sieve of Eratosthenes is the design pattern of a pipeline, of a concurrency pipeline, I would say. And then also a token ring example is here good to show a high number of this very limited system. This is only with 250 megabytes, so it's really an absolute ancient system for computer scientists. But we can let that run to see that this system with this very limited main memory of 200 kilobytes can run so many nodes, 200,000 parallel processes in a token ring setup where we have these nodes created and then the neighbors created with this mod operator to the symmetric neighbor and so on. And there's this traffic simulation that actually consists of plenty of modules. There's a XML reader and everything. That's what's here in this row. But I can't go through it, but may just shortly open. This is the main simulation with the cars offering a set of interfaces here performing. Here it's waiting for this virtual time, for example. And this is, but I don't have the time to go through it. I just want to show that there is the source code. And for the simulation, we have a certain set of input data delivered by the Swiss governments, which have the statistics of also having the Zurich network and also data of persons having a certain plan in mind to go for their work and where they plan to drive through. And these are a lot of plans, and I've just for here I have computed the simulation with 10,000 or something, 10,000 cars. Just that for to be able to do that with this time. And now I shift from the development system to my mini kernel, and this is just here. This is very it's coming. So it's very simple. It's a very simple interface. So at the top there's where you write your commands, and in parallel you can get output here. This can be textual or even graphical output. And I will now run first this simulation, which was this producer-consumer example. There won't happen much, just that these components are created. They're exchanging, like here, a million of messages via this bounded buffer. It's now already finished. And then we can say like show resources. Now we have 5 components in this system, and all processes are already completed here. And we see we have exactly 250 megabyte free memory. It's also on top, you see one process. It's a very old machine. And then we are able to, for example, delete this component with name X. And then we have, again, only one component and our memory back, except the code memory is cached here. We can also run this token ring example, which should have more resources. Here we see it's building this network, and then we now have 200,000 processes, and then this, of course, needs some memory, and then it's already finished. And the simulation I have let them run before, but I have something like an animator that shows you. It's also not so graphically impressive, but we show now the result of such a computation with the road animator that requires some code, some component code, and then connect this new road animator components of this simulation. This requires the file system, and the file system is an interface that is offered by the system component itself. That's the kernel itself. It also requires, we see in parallel here it's starting to read in this XML file via also such a parallel reader, and it requires some system time for performing the simulation, the graphical output simulation, and there's also a graphic view needed. That are all interfaces required by this program, so to say. So programs are also components. And then we see here it's this a zoom of this Zurich area, where you can figure out. Here's, I think, the central. Here's this Zurich Lake. Here's, I think, a bridge to what is it, Rapperswil? I'm not, but you. Oh, it's more right. And you see here the cars have this 10,000, only 10,000 cars are here displayed with such red dots, and we see here the time is simulated. But the simulation is actually, and this is not impressive, is just for calculating the simulation. It's not for viewing. Viewing is just for show purposes, so to say. It's just the simulation runs, computes this data, and then we'll deliver them again in a file that can then be used, for example, by this TU Berlin. And you will see here the Swiss are really early birds, so they work quite early. And there we see we have a lot of traffic here already for this few number of cars. And I think that's at least what I have prepared. And yeah, so thank you for your attention.
So,
Yes.
I was going to ask, have you tried simulating your language in runtime? It sounds like it looks like you just started from scratch here. Have you tried simulating this on an existing system?
Yes, that's what I've shown before. This one C++ simulation is the official, so to say, implementation of.
I mean, simulating your runtime.
No, this unfortunately. So to somehow have an emulator that runs my. No, unfortunately not. But I would wonder whether it can be executed, because it's like a kernel. It really starts. There's no Linux or something underneath. It could be executed. I hope so in a virtual machine, because otherwise the implementation of the virtual machine would be right, unless I have used some kind of hidden or unspecified functionality, which shouldn't be the case.
So in this case, if the process doing the graphic visualization turns out to sort of go really slow, because, I don't know, 200,000 cars are trying to sort of move, would that slow down the actual simulation? Or
no, the simulation is invisible. I could start this here, but this requires some more time, because these plan files are really excessive and need to be parsed. This would be. Yeah, but you can start it, but it's.
But how do you deal with the problem that you would run out of buffer space? I mean, if the simulation produces data without ever being stalled, if you like. And the graphics system that is consuming that data cannot follow when you just run out of buffer space eventually.
Yes, maybe. Here's like that this simulation of this graphics is kind of just using existing calculation results. But calculating, this is just non-graphical, then this just dumps down this data into a file. But this is true. These are not yet modeled as a pipeline of components. But then they would slow down, certainly, because the graphics is here not optimized. It's just very simple VESA mode and nothing particularly optimized. Also, the file system, that's the reason why it took a little bit longer to start this output, because these XML files need to be read, and it's actually the file system, or the disk access is very simple with PIO mode and not with data, or like I call it. No, this bus mastering support. But this is just questions of extending it's really the kernel with some, let's say, extensions to see something. Also, this font is self-designed, and so it's nothing particular with regard to that. But really, the focus was on this invisible, so to say, system building.
So what's next for you?
I don't know. Now I'm in Switzerland. I have a small company, but I'm open for any kind of a company of industrial business, like a software engineering and software design provider. But I'm open for any kind of this related.
I'm also wondering, you've built up a series of concepts here. Do you have ambitions to explore further on any of these concepts, or build this out beyond the current capabilities, or is this sort of like, hey, it works, I'm tired of it?
Yeah, this is difficult to say, because this was actually a work of a dissertation, and I'm now just, if there is a kind of a chance, of a finance chance, then I will certainly have interest in continuing it, and if not, then I can live with that. But it's also, I must say, for the elaboration, this thinking, it's like a tour d'horizon. It does not kind of harm if you think about such problems and go really deep, then you get a completely different view to this kind of mainstream perception of what is state-of-the-art programming, and then also gain, let's say, new input for also designing usual system like in industry, because then you have somehow know what is kind of the more profound conceptual basis, and what is a little bit like the provisional solution, and should a little bit avoid it.
All right.
Thank you very much.